Hi everyone and welcome to this next lecture in the NPTEL course Machine Learning for Core Engineering Disciplines. In the last class we have discussed about the vanishing gradient problem while working with deep neural networks and how that happens if we use the tanh or the sigmoid activation functions, and it is because when these activation functions and their derivatives keep on multiplying each other, then the value of the gradient keeps on decaying and going towards 0. We discussed how the ReLU activation function, the rectified linear unit, can deal with this problem. So today what we will discuss is third in the series of problems when we work with neural networks. The first was overfitting, for which we learnt a number of strategies like early stopping, dropout, weight decay, regularization and so on. Then we looked at the vanishing gradients problem. Today we will look at the third problem, which is the exploding gradients problem, and after that we will take up a simple example of a neural network to represent a logic gate that is encountered in computer science. So let us go ahead and get started with today's lecture. So as I said, we were talking about the challenges during deployment of neural networks, right, and we have already discussed two of these issues. The first one was overfitting, right, and I already explained how we deal with it, and the next one was the vanishing gradients problem, right. So now that we have looked at these two, today's lecture part of it is going to focus on the problem of exploding gradients, which is completely the opposite of the vanishing gradients, but this can also happen, and the problem with this is that you are going to have very unstable updates of the parameters during the gradient descent algorithm. So what happens in exploding gradients is that the gradients of the loss function they grow exponentially, particularly for the layers near the output layer, right, because the layers that are deeper into the network towards the input layer, they are sort of insulated, that is where the vanishing gradients occurs, but this exploding gradients is more towards the output layer, and this causes, like I said, unstable updates in gradient descent. During the gradient descent algorithm. Right, resulting in also large parameter values and failure of the optimizer to converge. Okay. So obviously if the gradient descent algorithm fails to converge, then you will not have the parameters that you will need for deploying the neural network model, right, and this therefore is a prominent issue, and the solution to do this, the solution to this problem is something known as gradient clipping. Okay. So what you do in gradient clipping is you specify a maximum allowed value of the gradient norm. right, which enables more stable gradient descent parameter updates. Okay. So, this is the one of the solutions. The other solution is, if working with recurrent neural networks, RNNs, right, you can explore other architectures. So, instead of the vanilla RNNs, you can use either the long short term memory, LSTM unit, or the gated recurrent unit. GRU, instead of the plain or vanilla recurrent neural network, and this could also solve the exploding gradients problem. Okay. So, this sort of ends the section wherein we talked about the practical challenges during the deployment of neural networks, and just as a reminder, in the case of overfitting we discussed various strategies, for example early stopping of the training process, right, based on the validation loss going up, you stop at that point, or you can have some kind of a regularization of the weights. So, this is also called weight decay. So, that is possible, and then there was another option which was dropout. Essentially you allow some of the nodes to become inactive, right, during the training phase, and that has to be factored during the inference phase of the neural network, and there is also other strategies like data augmentation. Okay. Now, with vanishing gradients we discussed that the ReLU activation function, ReLU, rectified linear unit activation function, is a good choice, because there the gradients do not really decay to 0, they remain stable if they are high, or again if you are using RNNs you can transition to LSTMs and GRUs, which were also solutions to the problem of exploding gradients. Okay. So, with this section sort of done, I will now come to the next part of this particular lecture, and that is about looking at a very simple neural network in action, right. So, trying to figure out what happens when you take a very simple neural network, and that will be a neural network with just one hidden layer, and we will see that with that one hidden layer we can actually incorporate a non-linear decision boundary. If you think of a classification problem, then we will be able to implement that kind of thing instead of just working with a linear decision boundary which happens in the plain support vector classifier algorithm or even the logistic regression algorithm. So, let us go ahead and see the simple example of a logic gate implemented through a neural network. So, the next topic is an example of logic gate, right, the OR logic gate as a neural network. Okay. Now, what are logic gates? I mean, many of you would know about it conceptually. Logic gates are basically the AND, OR and NOT, those kind of operations which we use in computer science, whereby you try to combine two logical operations, right. You want to find out whether two conditions are simultaneously met, or whether only one of them are met, or if none of them are met, right. So, basically these logic gates, right, are used in computer science. So, computer science is based on the application of logic gates. All operations at the end of the day right, are implemented through these logic gates, because everything on a computer is binary, right. Numbers are not represented using the decimal system like we do in our daily lives, but rather we use the binary system, and in a binary system everything is a 0 or 1, basically it is a boolean, and that is why if you use a logic gate you can implement operations like addition, division, subtraction, everything is at the end of the day just a logic gate on a computer. So that is why it is important to understand how these work and whether neural networks can allow us to understand, right, how these logic gates work. So computer science is based on the application of various logic gates such as, I just mentioned the basic examples like the AND gate, the OR gate, the NOT gate, and there are many others like XOR, which is basically exclusive OR. So exclusive OR means that only one of the two conditions should be true, not both together, right. Then you have NOR, which is basically NOT plus OR, and you have things like NAND, right, NOT plus AND, XNOR, right, NOT plus XOR, and so on, right. So there are various logic gates and all of these find use in different kind of operations. Now from the perspective of neural networks, it is possible to represent logic gates as simple neural networks. Right, with the Boolean variables or with the Boolean inputs as features, okay. And this also demonstrates the importance of hidden layers and activation functions. So both of these are important to represent logic gates as neural networks, okay. So for example, let us consider the OR logic gate. So corresponding to every logic gate you can have what is called a truth table, okay, a table that tells you under which scenarios the logic gate evaluates to true and under which scenarios it evaluates to false, right. So now in this case, like I said, right, the Boolean inputs are the features, right. So there are only two features here because these AND or OR gates, they work with two inputs, the NOT gate works with only one input, right. So these are the two inputs, and because these are booleans the only value they can take is 0 or 1, right. So there will be 4 cases, so either both of them are 0, one of them is 1, or both of them are 1, right. So these are the 4 cases, and the output, right, of the OR gate, so x1 or x2, so if any one of these values is true, that is 1, then the output is also 1, right. So if any one of these has to be true, so if x1 is 1 then also the output is 1, if x2 is 1 the output is 1, and if both are 1 then also the output is 1. The only scenario where the OR logic gate is 0 is when both x1 and x2 are 0, and then neither x1 is 1 nor x2 is 1, that is why the output is equal to 0. So I hope this makes sense, and obviously many of you, for many of you this would be very familiar. Now let us try to represent this, right, on the 2D plane, right. So there are two variables x1 and x2, so let us try to plot these values here. On the horizontal axis I will have x1, and on the vertical axis let us have x2. So what are the points here? First, in the truth table you have 0 0, right, which corresponds to false. So, I am going to denote false, which is 0 with a dot surrounded by a circle, right. So, this point here is false, right. The other false points are here. So, sorry, all the other points are true, right, because we are looking at the OR logic gate. So, all the other points are true, which corresponds to 1, and I am going to represent that as a cross marked by a circle, right. So, here you have 1 0, right, which will also evaluate to be true. Here on the vertical axis you will have 0 1, which is true, and finally 1 1 will also amount to true. Okay. So, these are the 4 points here, and this is the example of the OR logic gate. Now, in the OR logic gate you can see that you can create a very simple linear decision boundary that can separate the true and the false points. Consider, for example, this straight line here. All the points to the right of this line, they are true, and all the points to the left of this line are false, right. So, this line here can act as a linear decision boundary. Okay. Now, on the other hand, there are other logic gates, particularly the exclusive OR or the XOR logic gate, where it is not possible to have a linear decision boundary. So, let us go ahead and see how that particular logic gate works. So, we are going to take the example of a XOR logic gate or the exclusive OR logic gate, and in this case you will see that we will need a non-linear decision boundary to be able to separate the two classes of points, the true and the false points. So, again we will have x1 on the horizontal axis, x2 on the vertical axis, right, and in this case exclusive OR, right, it will amount to true only if only one of the two out of x1 and x2 are true, right. So, if both of them are false, then also you will get false here. So, this is 0 0, and if both of them are 1, then also you will get false. The only points that are amounting to true are the other 2 points, right. So, if you take for example here, this is 1 0. So, here this is exclusive OR. So, exclusively x1 is true and x2 is false. So, therefore, this point amounts to true. On the other hand, if you look at 0 1, then here exclusively x2 is true, and therefore, this point also amounts to true. So, this is the XOR logic gate, and in this case try as you might, you will not be able to draw one straight line which is going to be able to separate this into two different classes. For example, if you take this line, then you have both true and false above and both true and false below. So, clearly it will not work. You can try various other lines, and the only possible way in which you can try to make this work is, for example, to have a non-linear decision boundary, for example this, right. So, this is a non-linear decision boundary, and you can see that within this boundary you are having false values, and outside this boundary you are having true values. So, in this case you will be able to represent the logic gate through only a non-linear decision boundary. So, let us go ahead and write these points down. So, a linear decision boundary works for some logic gates. example the OR gate which we looked at, but it fails to separate the true and false points for other logic gates. Such as the XOR gate or the exclusive OR gate, and in this case you will require, one requires a non-linear decision boundary. And how is this non-linear decision boundary implemented as part of a neural network? Essentially you will have to rely on a hidden layer inside the neural network. So a neural network with a minimum of one hidden layer is required to implement the XOR logic gate. Okay, I hope it makes sense, right. Now what we will do in the remainder of the lecture is we will try to implement the OR logic gate via the use of a hidden layer. So in this case the hidden layer is not really necessary, but just as an exercise we will try to implement the OR logic gate while using a neural network with a hidden layer, right. So we are going to take the example of implementing the OR logic gate with a feed forward artificial neural network with fully connected layers. In machine learning parlance, this type of a neural network is also referred to as a multi-layer perceptron. Or an MLP. So a perceptron is a very simple unit that takes an input and then combines them linearly and provides an output, and of course here you are having multiple layers of perceptrons that you will be putting together. Now we will be implementing this particular multi-layer perceptron using a nonlinear activation function. So we will employ a nonlinear activation function, and the function we will choose is the ReLU activation function, the rectified linear unit, which is equal to 0 if the input z is less than or equal to 0, and it is equal to z itself if z is greater than or equal to 0. And if you remember, in other words, you can simply write this as max of 0 comma z. That is how you can represent the ReLU activation function. So let us go ahead and see how we can implement the OR logic gate with a multi-layer perceptron involving the ReLU activation function. Okay. Now I will give you an analytical solution here in terms of all the nodes and all the weights, but you are free to implement this, right. Once we will teach you how to implement neural networks in Python in one of the subsequent lectures, what you can do is you can go and specify the architecture of the neural network and then let the computer through the gradient descent algorithm figure out the weights and the biases, right. So then you can use there will be 2 features in the input layer, and then even in the hidden layer you can use 2 nodes, and then you can have an output layer. Here for simplicity I am going to just have one node in the hidden layer. Okay, so let us draw the architecture of the neural network with the hidden layer. Okay, so you are going to have 2 nodes in the input layer. So let these be x1 and x2, and these are going to feed to the only node in the hidden layer, which is essentially z1 2, and you know that the superscript 2 stands for the layer number. So this is the second layer, and this subscript stands for the node number, and then finally you have the output, which is the y. Okay. Now this is a very simple architecture, so you can try later, right, implement in Python training of an FFNN with 2 nodes in the hidden layer to represent an OR logic gate. Okay. So like I said, for analytical simplicity here we will only work with one single node in the hidden layer, and by now you know how to write down the output of the neural network. You work right from the output to the input layer. So at the output layer you simply say that the value y, that is the activated form of z12 and z12 times a weight and a bias. So let me erase that, is the activated form of w112 times z12 plus the bias term. So essentially you know this notation. In the notation the subscripts, right, the second subscript tells on which node it is acting. So it is acting on the first node, right, that is the 1 and 1, and then it is contributing to the first node in the next layer, right, and the layer number on which it is acting is written as a superscript, that is the convention we are following in this course, times z12 plus b12. So then this b12 means the bias, right, of the first node, right, in the next layer, right. So the layer current layer is the second layer, so the next layer will be the third layer. So this is the bias term as it feeds to the first node in the next layer, the third layer. Okay. So with this written, now what we can do is this z12 itself is going to be formed by the weighted forms of x1 and x2. So that will be g of w112 times the activation function applied on w111 x1 plus w121 x2 plus b11, and then you still have b12 here. Again, to explain the notation here, your first feature, right, so this is specifying the weight of the first feature as it feeds into the first feature in the next layer. So that will be the second layer, and this is the weight of the second node, right, as it feeds to the first node again in the next layer, and this is the bias contributing to the first node in the next layer to the first layer. Okay. So I hope this makes sense to you, how we have written down this expression, and in one of the earlier lectures I had told you that this weights can essentially be written as a matrix, and that makes everything easy because you can apply linear algebra. So here the weight matrix corresponding to the first layer is simply w111 w121, right. So it is a 1 by 2 matrix, right. Why? Because the first layer has 2 nodes, as you can clearly see in this diagram, and the next layer has 1 node. So, the size of the weight matrix is the number of nodes in the next layer times the number of nodes in the present layer. And similarly you can write that the weight matrix corresponding to the second layer is simply a scalar, right, because there is one node in the next layer and one node in the current layer for the second layer, right. So, this will be W112, right. Now, I am going to give you the solution, right, I am going to give you the numbers corresponding to these weights, right. However, if you did training, right, you will find out these numbers, right. So, this is -1 -1 and this is also -1, okay. In addition we have to specify the biases, right. So, the bias, right, from the first layer, right, there is only one node in the next layer. So, bias in the first layer contributing to the first node in the next layer is 1 and the bias in the second layer as it contributes to the next layer is just 1, okay. So, now if you plug in these values here you will be able to write that y is g of W112, that is this, right, -1 times g of W111, right. So, that is -1 as well plus W121, that is also -1 plus the bias term B11, that is 1, and then you will have B12 that is also 1, okay. So, finally, right, we have been able to write y which is a function of x1 and x2, right. The output is essentially g of 1 minus g 1 minus x1 minus x2, okay. And like I said, in this example the g's here they are the rectified linear unit, okay. So, now let us see if we have if this proposed multi-layer perceptron is actually able to do the job, right, because ultimately we need to achieve this truth table for the OR logic gate, right. Only if this truth table is achieved we have a multi-layer perceptron that can represent this particular logic gate. So, let us see if that works out. So, now let us evaluate y 0 comma 1, right. In this case you know that the OR gate should give the value 1, right. So, this output will also be the same as y10. How can I say that? That is because the way in which x1 and x2 appear is very symmetric, right. There is a minus x1, there is a minus x2. So, this expression is symmetric with respect to x1 x2. So, I can clearly say that the output will be the same whether it is y01 or y10. So, if we plug in the numbers here, let us see what happens. This will be g of 1 minus g 1 minus 1 minus 0, okay. So, that will be g of 1 minus g of 0, okay. And you know that the ReLU activation function, I had already written this here, is z if z is greater than or equal to 0 and it is 0 otherwise. So, this g of 0 is simply 0. So, this becomes g of 1 minus 0. So, this is g of 1 and g of 1 you know is 1, okay. So, this actually works, right. So, this corresponds to the second and the third rows in the truth table, okay. So, so far so good. Now, let us see what happens when you have other inputs, okay. So, if you have y11, that will be g of 1 minus g 1 minus 1 minus 1. So, So that becomes g of 1 minus g of minus 1, that is g of 1 minus 0, which is g of 1, and that is also 1. So when the input is 1 comma 1, then also the output is 1, and finally you can test the last case, which is y 0 0. So this is g of 1 minus g 1 minus 0 minus 0. So that is g of 1 minus g of 1, and you know that g of 1 is 1, right. So that becomes g of 0, which is simply 0. So this means that the proposed multi-layer perceptron, right, is able to represent the OR logic gate, right. So the proposed MLP architecture weights and biases faithfully reproduce the output of the OR logic gate. Okay. Now I encourage you to try to represent other logic gates like OR, AND, NAND, NOR, XOR and so on also as a neural network. It is a fun exercise, you can do this analytically, but also you can implement this in Python like I have suggested here. You should be able to do that after a few lectures when we have a tutorial on implementing neural networks in Python. Okay. So this brings me to the end of this particular lecture. In today's lecture what we did was we finished the challenges associated with training and deploying neural networks. In particular we looked at the exploding gradients problem, and we said that the solution to it is basically to clip off the gradients, to have gradient clipping wherein you prevent the norm of the gradient from becoming too high. We also said that if you are using a recurrent neural network you can switch on to newer architectures like LSTM and GRU. GRU is from a decade ago and LSTMs are now almost about 2 decades old or 3 decades old. And then we moved on to the example of representing logic gates through neural network, and through the architecture and the weights and the biases I specified we were able to work out the outputs, and we saw that it did match the truth table of the OR logic gate. So this completes the lecture today. What I will do in the next lecture is start with recurrent neural networks. Thank you for joining today and I look forward to seeing you next time.